Hello viewers, a warm welcome to all of you. In this segment of digital communication, we are going to discuss something more about the matrix. In this segment, we are going to discuss matrix like Hermitian, skew Hermitian, symmetric, and skew symmetric matrix. They are required in the course to study well digital communication. Also, these concepts are important in any of the competitive examination. So let us start our discussion today. This is totally conducted by Gannon, powered by Wishbag. So first we are going to discuss a Hermitian matrix. A matrix is said to be Hermitian matrix if original matrix is equal to its conjugate transpose. That means mathematically matrix A is equal to A conjugate transpose. Notation is A Hermitian or A to the power H or AH. Let us take an example. Say matrix A is equal to P A plus IB in the first row. In the second row, A minus IB Q. Then what is the conjugate of the matrix? The conjugate of the matrix A is A star or A bar is equal to, in the first row, P A minus IB, in the second row, A plus IB Q. So what is the conjugate transpose? It is simply A bar to the power T or transpose or A Hermitian is equal to P A plus IB in the first row and in the second row A minus IB Q. It is simply equal to the original matrix. Hence, it is known as Hermitian matrix. Let us take another example. Say a matrix A in the first row is 5, 7 plus I, 6. In the second row, it is 7 minus I, 8 I. In the third row, 6 minus I, 3. What is the conjugate of the matrix? Try. Okay, check your answer. It will be A bar is equal to 5, 7 plus I bar, 6 in the first row. In the second row, 7 minus I bar, 8 I bar in the second row. In the third row, 6 minus I bar, 3, which is equal to 7, 7 minus I, 6 in the first row. In the second row, it will be 7 plus I, 8 minus I. In the third row, it is 6 I, 3. Hence, the A Hermitian or AH is 5, 7 plus I, 6. In the second row, it is 7 minus I, 8 I. In the third row, it is 6 minus I, 3. It is nothing but your original matrix A. Now let us discuss the properties of the conjugate transpose. If A and B are complex matrices and K is a complex number, then the following properties are true. That means A conjugate conjugate is equal to the original matrix A. A plus B conjugate, that means whole conjugate, is equal to A conjugate plus B conjugate. K A conjugate is equal to K conjugate A conjugate, where K is any complex number. And A B whole conjugate is equal to B conjugate A conjugate. A complex matrix A is called unitary if A inverse is equal to A conjugate. Let us take one example. Say capital A is equal to half in the first row, 1 plus I, 1 minus I. In the second row, it is 1 minus I, 1 plus I. Then what is A star? That means if you multiply these two matrices, it will be half into 1 plus I, 1 minus I in the first row. In the second row, 1 minus I, 1 plus I into half the first row, 1 minus I, 1 plus I. In the second row, 1 plus I, 1 minus I, which is equal to 1/4, 4 0 in the first row. In the second row, it is 0 4, which is nothing but identity matrix I2. Therefore, A star is equal to A inverse. So you can conclude that A is an unitary matrix. So points to be remembered here that if A is an Hermitian matrix, then eigenvectors corresponding to distinct eigenvalues are orthogonal or independent to each other. Number 2 is A is unitary diagonalizable. And number 3 is if A is a Hermitian matrix, then its eigenvalues are real numbers. Now discuss comparison between Hermitian and the symmetric matrix. The first is in symmetric matrix, eigenvalues of A are real. Also, in the Hermitian matrix, eigenvalues of the A are real. The second comparison is eigenvectors corresponding to distinct eigenvalues are orthogonal. In case of Hermitian, eigenvectors corresponding to distinct eigenvalues are also orthogonal. In the third number is there exists an orthogonal matrix P such that P transpose AP is diagonal. And in Hermitian, there exists an orthogonal matrix P such that P conjugate AP is diagonal. In linear algebra, a square matrix with complex entries is said to be skew Hermitian or anti-Hermitian if its conjugate transpose is the negative of its original matrix. That means mathematically A Hermitian is equal to minus A. Let us take an example. Say capital A is equal to minus I, 2 plus I in the first row, in the second row minus 2 plus I 0. Therefore, minus of A is equal to I minus 2 minus I in the first row, in the second row 2 minus I 0. And A transpose is equal to minus I minus 2 plus I in the first row, in the second row 2 plus I 0. Hence, A transpose conjugate is equal to I minus 2 minus I in the first row, 2 minus I 0 in the second row, which is nothing but minus of the original matrix, that means minus of A. Let us discuss the properties of a skew Hermitian matrix. The number one property is the eigenvalues of a skew Hermitian matrix are all purely imaginary and possibly zero. Furthermore, skew Hermitian matrices are normal. Hence, they are diagonalizable and their eigenvector for distinct eigenvalues must be orthogonal. Number 2 is all entries on the main diagonal of a skew Hermitian matrix have to be purely imaginary, that is on the imaginary axis. The number of the 0 is also considered as purely imaginary. Number 3 is if A and B are skew Hermitian matrix, then small a capital A plus small b capital B is skew Hermitian for all real scalars of small a and small b. Next is A is skew Hermitian if and only if IA is or equivalently minus IA is Hermitian. A is skew Hermitian if and only if the real part, that means R of A is skew Hermitian, skew symmetric, and the imaginary part IA is symmetric. If A is a skew Hermitian, then A to the power k is Hermitian if k is an even integer, and skew Hermitian if k is an odd integer. And A is skew Hermitian if and only if x Hermitian ay is equal to minus y Hermitian ax for all vectors of x and y. If A is a skew Hermitian, then the matrix exponential e to the power a is unitary. Now let us discuss decomposition into Hermitian and the skew Hermitian. The sum of a square matrix and its conjugate transpose A plus A Hermitian is Hermitian. The difference of a square matrix and its conjugate transpose A minus A Hermitian is skew Hermitian. This implies that commutator of two Hermitian matrices is skew Hermitian. And an arbitrary square matrix C can be written as the sum of a Hermitian matrix A and a skew Hermitian matrix B. That means C can be written as A plus B, with A is equal to half C plus C Hermitian and B is equal to half C minus C Hermitian. Now let us discuss symmetric matrix. A square matrix A is said to be symmetric if small a ij is equal to small a ji for all I and j, where aij is an element present at ijth position, that means ith row and jth column in the matrix A, and aji is an element present at jith position, that means jth row and ith column in matrix A. In other words, we can say that matrix A is said to be symmetric if the transpose of matrix A is equal to the matrix A itself, that is, A transpose is equal to A. Let us take one example. A is equal to, that means capital A is equal to 138 in the first row. In the second row, it will be 3, 8 minus 4. And in the third row, it will be 8 minus 4, 6. It is symmetric matrix because aij is equal to aji for all I and j. Here, a12 is equal to a21 is equal to 3, and a13 is equal to a31 is equal to 8. Also, a23 is equal to a32 is equal to minus 4. In other words, the transpose of matrix A is equal to matrix A itself, as discussed earlier. That means A transpose equal to A, which means matrix A is symmetric. Now let us discuss the skew symmetric matrix. In this case, a square matrix A is said to be skew symmetric if aij is equal to minus aji for all I and j. In other words, we can say the matrix A is said to be skew symmetric if transpose of matrix A is equal to negative of matrix A. That means A transpose or AT is equal to minus A. Note that all the main diagonal element in the skew symmetric matrix are 0. Let us take an example of a such matrix. Say capital A is equal to 0, minus 6, 4 in the first row. In the second row, 6, 0, 7. In the third row, it will be minus 4, minus 7, 0. So, what is A transpose? Check your answer. It will be 0, 6, minus 4 in the first row. In the second row, it will be minus 6, 0, minus 7. In the third row, it will be 4, 7, 0. And minus A is equal to 0, 6, minus 4 in the first row. In the second row, it will be minus 6, 0, minus 7. In the third row, it is 4, 7, 0. Therefore, A transpose is equal to minus A. It is skew symmetric matrix because, as discussed earlier, aij is equal to minus aji for all I and j. Here, a12 is equal to minus 6 and a21 is equal to 6, which means a12 is equal to minus a21. Similarly, the condition holds true for all other values of I and j. There are some important observations. What is the observations? For any square matrix A with real number entries, A plus A transpose is a symmetric matrix, and A minus A transpose is skew symmetric matrix. Second observation is any square matrix can be expressed as a sum of symmetric and a skew symmetric matrix. So, what we have discussed in today's lecture: Hermitian matrix, then we discussed skew Hermitian matrix, after that we discussed symmetric matrix, and lastly we discussed skew symmetric or asymmetric matrix. This lecture is little bit lengthy because of some important concept. That's all for this segment. Practice this segment repeatedly with all the examples. And stay safe, stay tuned to Ganon. Bye.